I'll give it an introduction. So,
Yeah, if you want to.
hi guys. So this is Russel. We're going to be giving a talk on FEA and numerical integration.
Yay! Right, so let's get this slide. Thanks. Okay, so hi, my name is Russell. Real quick about me, I'm a first semester PhD student in the computer science department studying stencil methods with Russel Chowdhury. Before I came back to my PhD program, I was mostly working as a software engineer, and most of what I'm talking about today was what I was working on at this place, Intact Solutions. The other thing to mention is, although I did get an undergrad degree in math, I am not a mathematician, so please don't expect the rigor and depth that maybe you would get in other lectures. My goal here is to sort of give a higher level story, narrative about a topic, maybe introduce you all to some vocabulary, show you all what other folks are working on out there. We're not going to be looking at theorems or proofs or anything like that today. Sorry to disappoint. So, what are we talking about today? The main thing that I would like to introduce to y'all is this set of techniques called finite element analysis. I hope that at the end of this talk you'll have a rough idea on what it is, what people use it for, and roughly how it works at a high level. It does turn out though that it involves computing a lot of integrals numerically. So we're going to look at something called quadrature, which is how we do that. And really that's it. Hopefully I can bring this in a full circle and show that by manipulating quadrature we can avoid some difficult bottlenecks in the typical finite element workflow. And then we're going to conclude / have an intermission, and if folks are interested afterwards, I have some bonus slides about research that we've done at Intact Solutions that allow us to kind of do some nifty things with finite element analysis. So, at a high level, what are we talking about here? Finite element analysis is a framework of techniques for solving differential equations, like numerically solving differential equations. Typically, this means over geometric domains, so like designed or manufactured parts, for example. So some typical examples of the kind of problems that you might use finite element analysis to solve would be something like linear elasticity, where you're solving for a field called displacement, which is sort of an infinitesimal version of deforming an object under load. So you'll see this show up in structural engineering, if you want to see if a building can handle the weight, or if a bridge is going to collapse. Thermal transfer problems or thermal equilibrium problems are also really common. So, given a heat source and some different cooling boundary conditions, what is the temperature field? That's what we'd be solving for. Finite element analysis also shows up in things like fluids, where you're solving for velocity fields. Big asterisk there, though. Fluids are kind of a whole thing, so don't think about that one too much. The real thing that I want to start thinking about, though, is how do we represent these fields over some geometry, right? That's kind of the big question here, and we're going to talk about that more in the next slide. The really important part of finite element analysis, a lot of the equations to model this stuff are relatively simple. They're like conservation laws. So if you think about thermal equilibrium, you might have something like the Laplace operator. But everything gets way more complicated when you introduce boundary conditions, right? So if you have some, some geometry like this car or something, we might want to fix the displacement near zero at one part and apply some forces somewhere else, right? In general, we're going to fix the field value some places, we're going to fix the derivative of the field somewhere else, and by building up these boundary conditions with a suitable domain, you can really begin to model some interesting physical phenomena. And just a little bit of history, this is a really well-funded, pretty broad area of research. It started out in the 1940s looking at structural problems like bridges and other kinds of truss structures. And it really picked up speed in the 60s when NASA started using it. So the first software implementation of all this that was sort of widely adopted was called NASTRAN. You can still find it in use today. Of course, this is one of those things where the techniques and the methods were well underway and well in use before people kind of went backwards and sort of formalized it all and actually understood what it is they were doing. But as that process occurred through the 60s and 70s, these methods were generalized and applied to thermal problems and all sorts of other places, and it started to see uptake in the automotive industry and the aerospace industry and defense and all of that. And if you come to the present moment, where all of our computers are really powerful, you'll find that designers and engineers in a wide variety of industries have access to these kinds of methods, and you can probably also use them at home now too, which is pretty cool. So just to look at some examples here, because pictures are what it's all about. So we're going to kind of mostly be looking at sort of equilibrium problems, like not dynamic problems that change over time. But these techniques can be used to build up some really interesting nonlinear phenomena. So like here with this car crash, we have dynamics over time with large deformations. Variations, what I'm showing you today, can also be done to do frequency analysis. So if you want to find like the resonant frequencies of some part, that's what we're showing here. So it's like our crowbar with different resonant frequencies and like what the displacement looks like, kind of the waves traveling through. This stuff is really important in aerospace where vibrations and sort of a free body happen. I think it's also worth mentioning that numerically solving fluid flows, finite element analysis usually isn't the preferred method for doing that, but in computational fluid dynamics, a lot of it depends on the regime you're in, and it turns out that finite element analysis is really good at handling hypersonic fronts or shock waves. So you see it show up a lot when you're doing like blast simulations for explosions and whatnot. And so this last figure is actually from Lawrence Livermore National Laboratory. They fund a lot of research into this kind of stuff. All right. So I wanted to show you all a couple motivational examples just to really drive home like what we're doing. Oh, sorry. So first we're going to look at a heatsink example. So this is some geometry I have loaded up here, and we're going to try modeling this as a heatsink. And what I mean by that is we're going to apply, sorry, I should look at my screen. So we're going to apply kind of a fixed temperature down here to our temperature field. And then what we're going to do is have a large convection boundary condition. And what this is sort of modeling is the cooling effect of air over the surface, sort of thermal transfer between mediums. And I have a solution loaded up here. And this is kind of intuitively what you would expect, right? Like the temperature gradient kind of goes from warm near the bottom where we fix a high temperature to sort of cooler the further away we go. And that's interesting, but it gets really interesting when you look at the gradient of temperature, sort of heat flux, right? And this can give you a lot of information about how heat flows through the object, and this is really useful feedback when designing something like the heatsink, because we can see that maybe if we added more material here, where we have these high heat fluxes, maybe we dissipate more heat, right? And this is kind of the point I want to drive home, is that finite element analysis is really important in like the design and prototyping stage, because we could build this heatsink and test it in real life, but that's kind of expensive. So if we can validate a lot of prototypes virtually, then that's like a huge time and cost savings, right? One more example, just to really drive the point home. So here we have a mechanical part, sort of a bracket arm like you might find in a car or something. That doesn't really matter. And in this simulation, what we're going to do is we're going to fix the displacement, sort of the deformation, on these two surfaces. And then we're going to apply a force, a load, in the negative z direction here, right? So we're going to push the part this way. And again, I have a solution loaded here. And it's, again, about what you would expect. So displacement, unlike temperature, is a vector valued field, right? Like we can displace, any point could be moved in like the x, y, or z direction. And so here we're just looking at the magnitude. But we can actually kind of exaggerate displacement and animate this a little bit. And it sort of behaves the way you would expect, right? But again, if we look at the sort of derivatives, if you will, of displacement, we start to see something really interesting, right? Like this is where displacement is changing the most, and this can start to give us really interesting feedback about where we might want to strengthen our part. Strain isn't really a physical quantity. If you combine it with some material properties, you get something called stress. And stress is really, really important, right? Because stress will tell us a lot about like where our parts are likely to fail or tear. And so again, if we play through this animation, you can see like it makes sense. Like if we were going to do this real part, it would probably break right here, and that's captured really well by looking at the stress field. And so finite element analysis is very commonly used in structural scenarios like this for just this reason, where if you're designing a part, it's nice to like simulate it virtually, have an understanding of how it will behave under the loads that you specified, like what its failure points are, and that's what this tool set is really, really useful for. Does this make sense? Oh, hey, what's going on?
What software is that?
Oh, great question. So we're using, this is a program called ParaView. It's part of a suite of tools called BTK. It's really common in scientific visualization. So I ran these solutions in the software I was working on, Intact Solutions. We don't actually have our own like front-end application, so I mostly use ParaView to look at results. But you'd find ParaView in a lot of different sort of simulation suites that scientists would use.
It's licensed for free.
Oh, it's free. The software library behind this, VTK, is also free, but it's not very well documented. So the company that works on it makes their money by consulting. So it's like, oh, you want to use VTK in your project, you should hire us to teach you how to do it because we're not going to provide great documentation. But it's a fair trade-off, I suppose. Okay. Making good time. So to kind of do a really high-level sky view on like what the workflow looks like here. To start with, we need some geometry in the computer, and there's a very wide variety of ways that you can represent geometry in the computer. So CAD software, like an engineer or designer would use to design parts, typically works in like spline patches for the surface, so it sort of has this smooth representation. But having a triangle mesh of the boundary for some volume is also really common. That's pretty much how all video games work. A lot of CGI is done that way as well. There's also more exotic things like voxelized geometry. You might get that from a CT scanner or like Minecraft, I guess. Point clouds from LiDAR scanners, G-code that you feed into a printer. There's like a wide variety of geometry representations, but none of those ones that I mentioned are actually directly suitable for finite element analysis. We have to go on to the step 2 where we process it into a new kind of representation, a finite element mesh that's suitable for simulation. We also need to do some work to figure out like what physics we're trying to simulate, what boundary conditions we want, etc. And then in step 3 we have the solve step. And what this largely amounts to is building a really large system of linear equations, like a sparse system of ax equals b, running that through a sparse solver. We get our unknown solution field back, at which point we can visualize the results, analyze, do whatever kind of measurements we were hoping to do. Let's see, is there anything I missed here? Cool. So we're going to talk about that finite element mesh thing now. So earlier I kind of mentioned that question of like, how are we going to represent this solution field over our geometry? And the answer is piecewise polynomials. That's a pretty common trick in computing. So basically, what we need to do is we need to discretize our geometry into a finite collection of elements. That's where the name comes from. So if we have this this geometric domain, which we usually refer to as omega, we're going to break it apart. And so in 3 dimensions, tetrahedrons are really common, cubes are common. There's like a really big menagerie of finite element types that depend on how many degrees of freedom you want, etc. But we're going to kind of keep it simple. The really important thing to note, though, are these nodes that connect elements. And the reason those are important is twofold. First, that's where our solution values are going to live. So we're going to solve for like displacement or temperature at each one of those nodes, and then using something like Lagrangian interpolation, we're going to interpolate those nodal values over the element. And so collectively, this allows us to approximate this field anywhere in this geometric domain. Does that make sense? Because I mean, this is really like the most important detail of the whole slide, honestly. A little bit? Okay, cool. I probably should have pointed down here. Sorry, this pictures, or maybe should have blown them up a little bit to show on the projector. But in this example here with this wrench, right, we've solved for presumably stress, right? And we have stress at each of these nodes, and we're interpolating it using these elements. And so we can visualize the result in this way. So this is how we represent our solution fields. But the other thing that's really important is that during that assembly process, we have what are called test functions that also live at those nodes. And that large system of linear equations that we're going to build up, and I'll talk about that a bit more, is almost like an adjacency matrix. And the idea is that nodes that share an element are going to be neighbors in that matrix, in that graph. And so tracking the node connectivity is really important. The thing that if you were going to take anything away from this presentation, I think the main thing I want y'all to come away with is that this meshing process is the bottleneck of finite element analysis. It's what most practitioners of this spend most of their time working And that's for a number of reasons. So first of all, the number of elements we have in our mesh clearly has an impact on the quality of our solution, right? Like the more elements we have, the finer our resolution is going to be, the better we can capture all sorts of different effects and behavior. At the same time, having more elements greatly increases the computational expense of the rest of the pipeline. So it's sort of a trade-off, right? Like how many elements do we need to get the quality we want without blowing our computational budget?
How do you calculate that?
A lot of trial and error in practice, usually. Generally, what you'll, I'll try and like circle back to this point at a few places because there's a lot of follow-on effects that aren't, it's not like linear behavior necessarily, it's like you add elements, how it's going to increase your runtime. But generally, as you use a system, depending what your resources are, you'll have a pretty good idea of like how many elements you can handle in like the time frame that you want. But there's some other details, so I'll circle back to that. It's a good question. So one of the tricks here is that the traditional meshes assume that these elements are all full, right? And so we're not going to simulate directly on like the designed part, right? So you can imagine that if this geometry came out of some CAD software, it was probably modeled with like continuous smooth surfaces. But here we've discretized it into a bunch of tetrahedrons, so it's going to kind of have that like polygonal aesthetic, and that's kind of a trick too, right? Like the more elements that we apply, the better we can capture the detail of our original geometry. At the same time though, if we have really small details in our geometry, that's going to require a lot of elements in our mesh to capture. So there's like this anecdote from a study the Army ran where they had some huge part like a tank hull or something. And in the design part, in the corner, they had a little tiny stamp in it that had the part number. And that stamp has to be manually removed before it can be meshed, or else that little stamp would greatly drive up the number of elements we need to capture that detail. And so even before we get to any sort of like automation, usually there's a lot of manual intervention to kind of trim details that we don't want to bother simulating because we can't pay for that expense. All that being said, meshing algorithms have gotten really good. It's an active area of research. There are like multiple people in the computer science department working on this problem. There are certainly people in the mechanical engineering department working on this problem. But even still, in commercial settings, you're going to quickly run into geometries like an entire airplane where you can expect to spend hours to days just getting this finite element mesh. Like this is a huge computational bottleneck on top of the workflow issues of like needing to manually trim parts and whatnot. And so the full circle of this talk is like hopefully after we've looked at how we use numerical integration, we can come back to this and show one possible approach for simplifying this meshing workflow. All right. Any questions so far? Thanks for bearing with me, I appreciate it. Okay, so.
Here's a question.
Yeah, oh, hey, sorry. Thank you.
Sorry, just to clarify, did you say that the computational, the actual calculating of the mesh is the expensive part, or deciding on a mesh to use, which gives you realistic results but is not?
Yes.
Okay.
Certainly having, if you're starting with something that's already like a triangle boundary mesh, like you would find in like a video game or something, even taking that to a volumetric tetrahedral mesh can be quite expensive. But if you add on to that the additional factor of like, we need to decide how to approximate a smooth surface, like how many, because a tetrahedral mesh can be simplified to a triangular mesh on the boundary, right? Does that make sense? Mm-hmm. So even just finding what that triangular mesh is that represents some like smooth geometry, maybe like spline patches or implicit geometry, that can also be quite expensive to automate. And there you sort of have a dial of like how fine a resolution do I want to capture that smooth surface. Mm-hmm. Does that make sense?
Sure.
Fair enough.
Yeah, what's the big old complexity of meshing?
That's a great question. I think it's somewhere between n squared and n cubed, but again, it really depends on like where you're starting from.
Okay.
So a lot of the the problem of taking a triangular boundary mesh to a tetrahedral mesh is, I'm not going to say it's well solved, certainly there's still work to be done there, but a lot of the really interesting work you'll find is actually how do we get that triangular boundary mesh from an arbitrary surface. And there's all sorts of interesting techniques. There's a guy in the computer science department that's looking at using like Rishi flow to figure this out. So that's like one of the big areas, and I couldn't really tell you what the complexity of that problem is.
So are there like approximations so you can get the complexity down to like linear in terms of number of nodes?
Yeah, so hopefully I'll get to showing an example of how we might be able to do that.
Okay.
But one of the problems is like, how do you decide what details of your geometry are important, right?
Right.
So you have your input geometry, that's really like what this complexity is scaling with.
Okay.
And so if you can find a way to sort of ignore details automatically, then that can cut down on the expense.
Okay.
Cool, good questions. Okay, so if we go back, we're going to talk a bit about the solve step where we're building up that system of linear equations. This is a first pass. I think some of y'all will find this very unsatisfactory, and I don't blame you. I'll try and add more detail in a few slides. But essentially what we're going to do is for each element, and in this case I have a two-dimensional example where we're solving for displacement, right? So we've got these three nodes, and displacement in two-dimensional setting is, x and y, right? It's a two-dimensional field. So what we're going to do is we're going to get a linear ordering for our degrees of freedom, and we're going to build this adjacency matrix, this property matrix for the element. And this property matrix, kind of what exactly it is, depends on the physics we're solving. Commonly, you'll find it called the stiffness matrix because FEA is really deeply tied to structural analysis. But it could also be a conductivity matrix if we're studying a thermal problem. And so this is just trying to capture the material properties of the element in the context of the physics we're solving. And then we can sort of set this up in a linear system where we have our unknown field U, and then we have a load vector L. So that's where we're going to really capture the boundary conditions, like what forces are we applying, what heat fluxes are we applying. And if we solve this system, then we would get the unknowns just for this element, right? And so I think I mentioned this, but just to really drive home the point. In this case, we have three nodes, but each node has 2 degrees of freedom, right? And so that's why we have 6 entries in this matrix. And that really depends again, on the problem you're solving. So a lot of times in structural problems, you'll have 3 degrees of freedom for x, y, and z, but you could also add in different rotational degrees of freedom, so it can blow up pretty quick. And just to point out, this matrix grows n squared with the number of nodes in your element. And so when I mentioned challenges in meshing, different element types will have different numbers of degrees of freedom, and that's going to determine the density of these matrices. And it can blow up really fast. And then what we're going to do, typically you'll calculate those element matrices in isolation, and then what we're going to do is we're going to throw them all together into a big global system, a big global stiffness matrix. And the process is similar, right? We're going to take all the degrees of freedom in our whole mesh, and we're going to put them in a linear order so we can build up an adjacency matrix, right? And here we have kind of a one-dimensional example with temperature, where we have our 2 element matrices, and then it's kind of nice in one dimension because their ordering in space is their linear ordering, and so you can kind of see how we build a global matrix out of those 2 element matrices. In general, in a 3-dimensional problem, these element matrices are not going to be direct submatrices in here, right? Because the linear ordering that we use for the element matrix probably isn't going to be a subset of the global linear ordering. And so we're going to have to add those element matrices in element by element. But what you see is that you get these really interesting sparsity patterns. And there's solving these large sparse linear systems shows up all over the place in numerical methods. Sparse linear solvers are a really interesting problem space in their own right, and there's a lot of research into that. So in finite element analysis, usually you're using a very specialized linear solver that understands the structure of these matrices. So for example, in displacement, where we have 3 degrees of freedom per node, what we'll find is at the intersection of any 2 nodes, we have a little 3x3 matrix, right? And so the sparsity pattern is actually sparsity for a block, right? And a good linear solver in this domain should be able to utilize some knowledge about the structure of the matrix to sort of accelerate the solve phase. But once we solve this global system, what we have are nodal values, right? We have displacement or temperature at each one of those nodes in the mesh, and then we can do the post-processing or visualizing like I showed y'all earlier. The real question, and the reason I imagine y'all are finding this kind of unsatisfactory, is what are these k values? You know what I mean? How does that relate? The answer, of course, is it's kind of complicated. So I mentioned earlier that these methods were being deployed and being used in real world scenarios before people had a solid mathematical basis for what they were doing. Basically what you're going to do is you start with like what's called the strong form. That's like a differential equation like you're used to, typically like a conservation law. And then in finite element analysis, the preferred method to sort of get this into a form we can use is called the Galerkin method. Explaining that is sort of beyond the scope of what I want to cover today, but the general technique is pretty common in formalizing numerical methods. So basically what happens is we, oh my god. So basically what happens is we have our piecewise polynomial representation of our solution, and we're going to plug that into the strong form and then try and find the weights for that sum that will minimize the error, minimize the residual. What you'll end up with when you do that is sort of an integral form of your original equations. And so I wrote this really vague equation here. Like the exact form of this equation is going to differ quite a bit depending on what kinds of physics you're solving. In general, what we're going to find is that each element of that global matrix is going to be an integral over some element of some property times the derivatives of the two test functions that intersect at that point, right? And so if we go back, like that's a lot of bilinear integrals to compute, even for this simple element, right? So to fill out this whole matrix is going to require computing this kind of integral a lot. And so that's sort of part one on finite element analysis. Does anyone have any questions so far? Hope I'm not losing y'all. Hey.
So that P there is the piecewise polynomial for the characters.
I should have picked a different letter. So this is like our material property. So this would be like what the conductivity of the material is, or what the stiffness of the material is. But even there, it's like there's a stiffness is like a 6x6 tensor, and temperature or conductivity is just like a scalar field. And so like the exact form of these gradients is going to differ quite a bit depending on the kind of physics we're solving. So I kept this equation pretty big. But in general, we're looking at those test functions that we're using to interpolate. And for each element, we're going to look at pairwise each combination of test functions. And we're going to sort of try and capture the material property between those two test functions.
And then we just integrate it. So the sigma. Yeah. That one which just varies over the finite elements.
Yeah. So like here, if we were to look between like 1 and 2, right, we'd be integrating, like what's the stiffness between these two nodes within this whole element. And then the other thing to note is that maybe there's another element down here, but by the linearity of integrals, it's okay that we compute it piecewise, right? Because like if the whole domain for this integral is these two elements, then we'll do it one piece at a time and then add it into the global matrix. Okay. Good question. All right. So when we numerically solve integrals, which is what we're going to be doing here, almost always we do this through quadrature, which shouldn't be too scary because when y'all, I presume pretty much everyone here is taking calculus. So you've probably seen a Riemann sum, which is where you just fill in rectangles under a curve, and as the rectangles go to 0, you get the integral quantity, right? That's quadrature. The reason we refer to it as a quadrature rule is that it's a weighted sum of evaluating the function at certain points. And what we're really interested in are these weights and these points. And the idea here is that if we have a given quadrature rule, we have these weights and these points, then and we have the ability to evaluate this function, which is sort of a given, then we can carry that quadrature rule around and perform a bunch of integrals over this one domain and sort of swap out the function that we're integrating. And most commonly what you'll find is something called Gauss-Legendre quadrature. I hope I said that right. And these quadrature rules are sort of formulated, so like a rule of like degree n will be able to integrate a polynomial of like 2n minus 1 without error or something like that. So these are usually pre-computed rules, but the basic idea is that you have negative 1, and like maybe a degree, like degree 1 rule or something might have 3 points. Or what is that? sorry, this would be a degree 3 rule, right? And then if you wanted to, you know, create a rule like this for a two-dimensional space, you just sort of take the Cartesian product of the Gauss rule, Gaussian quadrature in one dimension, and you end up with something like this, right? The spacing isn't even, I sort of copied a table from Wikipedia here, but the basic idea is that even in like a 2 or higher dimensional case, we can use a quadrature rule like this to integrate over some polynomials and minimize the error of our approximation. Does that make some sense? Okay. Oh. No problem? Okay. Let me make sure I am capturing. Sweet. Okay. So, this is where we kind of return to our assumptions here, right? So we were saying that we're assuming elements are full. And so if we use a standard, if we imagine that we're using like square or cube elements, then we can think of this quadrature rule as sort of representing our mass density. And it's basically going to be equal to 1 everywhere, like it's constant and it's full. And so the challenge is, what if we don't have a full element, right? Like, you know, what if, right, so this rule will be able to integrate an element that's full of material, but like, what if we have an element where maybe it's only partially full? Then the challenge becomes, how do we find a quadrature rule that can integrate this partial amount of material, right? And there's sort of 2 ways you can think about this, right? We could create sort of a domain-specific quadrature rule, you know, where we only allocate points within the domain or whatever. Or maybe there's some way to manipulate the weights of this rule so that we can capture the integral properties of this partially full element. Yeah.
So, what's the definition of full or partially element?
Right. So, if we look at these like traditional finite element meshes, we're assuming that the domain captured by these elements is exactly the geometry that we're simulating over. And so in that sense, each one of these little tetrahedrons is full of material, right? Like if we broke this apart, then we would have just a bunch of solid tetrahedrons, right? If this was made of metal, then we'd just have a bunch of like fully metal little tetrahedrons, right? And the idea here is that this is conforming to our as-designed geometry. In this case, this element isn't conforming to our geometry, so we sort of have some void here, right? Like our test functions extend beyond our domain.
Okay.
Does that make sense?
Yeah.
Okay. Good question. And so this is kind of the full circle bit where at Intact Solutions what we do is we build a non-conformal mesh. We just immerse the geometry into a grid. And then we build specialized quadrature rules for these partial elements, and that allows us to get rid of this meshing problem. Because it's very, very cheap to essentially figure out what, you know, grid cells are going to be full with geometry and which ones aren't. And then if we have solved this problem of finding new quadrature rules, then we have a finite element mesh that's much cheaper to compute. And once we have our solutions, even though, you know, we could ask for the value of the field here, that wouldn't really make sense. We can always sample within the domain, and that would make sense. And so we can project our solution back onto the original geometry. So to show you what I mean a little bit here, in this part, the actual mesh we simulated on looked like this. And so a lot of these elements on the boundary actually have a lot of void in them, right? Like they're not all full. But once we have the nodal values on these, grids, we can always use interpolation to get the field quantity back on the original geometry. And so this is sort of the secret sauce of the place I was working at. And this allows us to like have a fully automated finite element pipeline that sort of skips a lot of this computationally expensive meshing stuff that people have to worry about. All right, that went a little faster than expected. This is where I wanted to wrap things up for those that have had enough, which is totally fair. Hopefully you have some understanding of what finite element analysis is for, where you might use it. a little bit on how we might use quadrature rules to numerically solve some integrals. If anyone's interested, I could talk a bit about moment fitting after, but I kind of want to call it here for everyone who's not interested. Oh Lord, I'm going to have to commit, huh? Does anyone have any questions? That went a little fast.
So,
Wait, in the middle of like a presentation, like you said, like some professor like using
Resheet
sheet flow, like
Yeah.
using for like
Yeah.
finding.
I can pull up this page after, but Dr. Gu in the computer science department. Pardon? Yes. Yeah. The very same. Yeah. I couldn't tell you a whole lot on how that works, to be honest. It's a bit out of my wheelhouse, but yes.
can we go back to the previous one about the grid line?
This one?
Yeah, so when you said like merge geometry and then analysis grid, like, so like, do you just take the cubes that the whole grid got, like you only take the cubes that is full and then you just ignore the cubes that are...
Yeah, so what I think I see what you're asking. So there's sort of this implicit grid, like some cell sizing. So we have one dial to decide how many elements we want.
Right.
And then, depending on the geometry representation, there are different ways of doing it, but basically we're going to scan through this grid and see which ones of these, which of these implicit cells has material in it. And then the collection of all those active cells becomes our mesh. And this mesh doesn't conform to the geometry, so it's much cheaper to compute.
So you would just ignore those cubes that are, just partially full.
No. The partially full ones are very, very important. It's the entirely empty ones that we ignore.
Sorry.
No.
So like the amount of detail will be depend on like how small will we set the cubes to be.
Exactly. So what's interesting about this method compared to the meshing algorithms I showed earlier is that we just have this one cell size dial to decide how much resolution we want in our solution, and it's entirely independent of geometric detail, because we can always capture any mismatch between geometric detail and the size of our grid, we can capture with an appropriate quadrature rule when integrating.
Can we construct it by some other kind of geometry instead of cubes?
Yeah. You could do something similar with like tetrahedrons or something for sure. Actually, I stole this figure from a paper from like 2020 that was like a pretty fancy new tetrahedral meshing algorithm, and the basis of that algorithm is actually immersing the geometry in like a tetrahedral grid, and then eliminating tetrahedra that are outside of the geometry.
Because there's some paper that I read before about like body with constant radius and therefore loop and stuff like that. It's kind of good. I'll try this.
Sounds good. Okay, y'all actually want to see more slides? Yeah. Oh, all right. Okay.
I have a question.
Yeah.
So this seems like you prefer to use the square mesh, right? But I've heard that many people also use the triangle mesh. So what's the difference between a square or a triangle?
Good question. So I'm going to throw in another term called an axis-aligned bounding box. So having an axis-aligned cube is very cheap to manipulate on a computer, more so than even like a tetrahedron. People who do meshing, like traditional conformal meshing, prefer tetrahedrons. It's much easier to take geometry, form a triangle mesh on the boundary, and then make a volumetric tetrahedral mesh. And so if that's the workflow you're going with, tetrahedrons make a lot of sense. But if you're looking to just immerse the geometry into some elements and have them be partially full, cubes make a lot of sense because cubes are just very easy to like index, and you can just use integers, and it's a lot simpler. Does that make some sense? There is some trade-offs though, right? Because the cubes are going to have you're going to have like a sort of a denser global matrix, right? Because you have more degrees of freedom in a cube element than you would in a tetrahedron.
Yeah.
And so one of the follow-on effects that we were mentioning earlier about like how expensive is this whole pipeline, the sparsity pattern of your matrix has a profound effect on how long the linear solve takes. And the linear solve can be very, very expensive. In our software at Intact, the linear solve is the bottleneck. And so what you'll find is that like geometry with like a very high aspect ratio, like a really long I-beam, is going to generate a sparsity pattern that a lot of the iterative solvers don't really like very much. And so another reason you might prefer tetrahedrons is that you're going to, it's going to generate a very different sparsity pattern than using like a cube element or some higher order element that has more degrees of freedom attached to it.
So your polyhedrons have like more nodes and it's like more complicated.
Yeah, because like another thing that I didn't really get into, so you know, if you have in like 2 dimensions, if you have the square, you know, this would be typically called like a first order element.
Okay.
But what you'll commonly find is people will have elements that are also squares, but they'll introduce like an extra set of degrees, like extra degrees of freedom to it, and this would be a quadratic element.
Okay.
And that comes from like the degree of the polynomials we're using in interpolate.
Okay, got it.
And so this element can capture, like using quadratic interpolation can nicely capture a lot of phenomena that like a linear element couldn't, but like this is way more expensive when you look at the sparsity pattern because of how much denser our global matrix is going to become.
Yeah. So how do you decide like how much approximation error you want to have? Like is it more like trial and error? Or?
Yeah, I mean there are people who study the theory of this, there are people like me who are like software engineers who implement it, and then there's a lot of mechanical engineers who are like practitioners who actually like apply these tools. And I can't even begin to judge like all the heuristics and like domain specific knowledge that goes into that. But it is very difficult to like fully automate this process because you do kind of have to have some intuition on like what level of accuracy is appropriate.
Oh, yeah.
And so in general, like the rule of thumb with our method is like if you're a designer and you're just trying to rapidly explore space, like use really big elements. You'll kind of get coarsely the right behavior. But if you're trying to validate a part that's close to production, you should really crank up the number of elements and make sure you're capturing all the fine detail and like the stress field and stuff.
Right, makes sense.
Yeah.
So are you always working with like homogeneous distributions of like meshes? Say?
That's a very interesting question. So,
Is it? I mean, you said you weren't studying dynamic systems.
so I think there's a bunch of ways to answer your question. So like one assumption here is that this property is constant. One of the things that we do at Intact is like, what if you have like a spatially variable material field, right?
Yeah.
Like, so for example, I mentioned CT scan data from like, you know, like if you wanted to simulate like the structural properties of bone,
Yeah.
then it's like you have a variable density field and you need to capture that in your integral. As far as like non-linearity goes, linear elasticity, so there's like this thing called the stress strain curve when you look at material properties, and usually a large chunk of that regime is roughly linear, but you can quickly enter sort of non-linearities like plastic deformation, where it's not like a perfect spring, it doesn't come all the way back, right? And in that case, you're probably going to need to approximate it with a number of like linear operator steps to, like if you sort of capture a plastic deformation or a non-linear deformation, you can approximate it with like a number of linear approximations in a row.
Now this isn't the case where you are having a dynamic mesh.
Yeah.
Well, like let's say in the case where you have you're solving the heat equations, like your physical mesh is not moving.
Yeah. So
Like
the heat
there is a
example was like
response, yeah.
equilibrium at rest.
Yeah. Okay. Yeah. So, like I guess in the there was a little bit of an animation on the end.
Oh.
I'm not asking about that, but I'm saying like you don't necessarily need to.
No. Yeah, I should clarify that. That's a good question. So displacement, like we're looking at in linear elasticity, like I said, it's kind of an infinitesimal representation of deformation.
Yeah.
But because in computer graphics we're all hacks
Yeah.
and just like want qualitatively,
Yeah.
so we can exaggerate it
Yeah.
and apply the displacement to transform something.
So I guess my question is, like, do you ever have a case where you're continuously updating a map to have, like, a time?
Yeah. So, oh, sorry.
And in which case you would need a non-homogeneous distribution or some way of mapping a non-homogeneous.
Yeah. So if you're gonna do something like this, where you're like doing car
Yeah,
crashing,
that's good.
then as you time step, you're absolutely right. Like your underlying discretization is going to have to transform over time, right? Like we probably couldn't capture this phenomena with a mesh of the car that didn't transform. That would be really difficult.
Yeah.
So every time step, we're going to have to apply that deformation to the mesh, redo the assembly, redo the whole step, and then like that's one little step through time. So we discretize time in that way. I feel like I'm not
You
quite
start with an initial discretization of like cubes or something, but as you evolve in time, you okay.
Yeah. And the same thing happens in like fluid flow.
Yeah.
So with like an example like this, what they'll typically do is they'll use like much higher order elements, kind of like that or larger, and you'll run it for a few time steps, but then what will happen is as your elements kind of start to deform, they might start to like overlap or cross each other, at which point you need to like remesh the domain. But up to a certain point, you can kind of like work your elements and it should be fine.
This is, you use this for, like this is commonly used for, well you said it's used for stuff with a boundary effect in the fluid.
Yeah, well, so with fluids, it's most often applied to like shockwave propagation.
Yeah.
Usually with fluids, you'll use something like finite volume method where you're like looking at flux across boundaries. It's similar, but doesn't necessarily have the splittable solve set
Yeah,
you
no,
usually do with local behavior. Sorry.
Sorry, just saying, I can see where you go with that. Yeah, cool. Thank you.
No worries. Okay. All right, I am not as well prepared for this part of the talk, but we'll give it a test drive. So the trick at Intact is we use moment fitting, and this shows up in statistics, this shows up in physics a lot, and it turns out that those Gaussian quadrature rules that I presented earlier are also the result of this moment fitting idea. And the basic idea here is that we want to have some simplified representation of the integral properties of some field, right? So if we're looking at like mass density, we want to sort of capture this mass density field without having to allocate a bunch of special quadrature points. And so what we're going to do is we're going to project our property field, like mass density, onto a polynomial basis. This is a different polynomial basis than the one we're using in finite element analysis. So we're two different kinds of basis functions we're talking about here. We're talking about moment fitting basis functions right now. And so what we're going to do is we're basically going to take compute this kind of integral for all of these different basis functions, and we're going to throw them in a vector. And the hypothesis here is that this moment vector is a very compact representation of the integral properties of some field in an element. And so if we can get this moment vector, what I'll show you is how we can use that moment vector to then fit a quadrature rule like this with appropriate weights so that we can integrate arbitrary density fields in an element. And then we'll look at like a couple ways in which like that's something you would want to do. Yeah.
So the mass density field would be like kind of analogous to like a probability density function for statistics.
Exactly.
Okay, got it.
Yeah. So the main takeaway from this slide is if we have some integram that we can represent as a weighted sum of these polynomial basis functions, these moment basis functions, then it turns out that we don't need to know the weights beforehand, right? If we can compute the integral of those basis functions over the domain, then we can fit the weights afterwards. That's basically all this is trying to say. So here I'm just like taking the integral of f over some domain. We plug in f with like that weighted sum of basis functions. We can pull out the weights, and we're just left with the sum of the integrals of those basis functions over that element. And because we can do that, we can set up, and again, this is a different linear system than the finite element linear system. If we have the moment vector, and we, in some given quadrature rule, probably a Gaussian quadrature rule, and we've evaluated those moment basis functions at each of those points, then we can solve for the weights of the rule that will represent the integral properties of this moment vector. And so again, if we can come up with this moment vector, then we can use this linear system to fit these weights to capture an arbitrary material field. So, just a little pop quiz. Does anyone want to take a guess on how we might compute an integral like this over a domain? Quadrature? So, in the first example here, I've been talking about CT scan data a lot. These data files are huge, like millions to billions of data points. And so we're not going to have millions to billions of finite elements. That would be unreasonable. So what's actually going to happen is we're probably going to have thousands to tens of thousands of these voxels per element. And voxels are nice because voxels kind of are like a quadrature rule, right? Like they are a little weighted sum over space. And so we could just use the voxel geometry directly to get like a geometry-driven quadrature rule. But as I mentioned, we have to compute those bilinear sums, like we have to compute a lot of them. And if each time we're computing them, we're performing a sum over tens of thousands of points, that's like computationally intractable. And so what we can do is we can use that voxel-driven quadrature once to compute the moments. We can compute this integral with the quadrature from the voxel geometry, and then we can use this moment vector to fit a much smaller quadrature rule that still kind of captures the integral properties. It's sort of like integral compression, if you will, right? Like we can approximate the integral of this really large voxel geometry with a much smaller quadrature rule, but actually retain a lot of the key detail. So it's an approximation, but in practice it works really, really well. And so by doing this, by capturing the moments of this voxel geometry in each element, we can then use those moment fit quadrature rules to do our finite element analysis, and this works out pretty well. In practice, meshing algorithms completely fall apart on something like bone. I don't know if you've seen like the inside of bone, it's like a foamy structure. That's like intractable to mesh with traditional methods. But all we really care about are the integral properties of that material. And so we can capture that integral property, those integral properties of moments, and then we can use the moments to do all the integration we need for finite element analysis. And then if we want, we can always project the solution back onto the voxels, and that's relatively cheap. Does that make some sense? A little bit? Okay. So here's another example. This one's a little bit trickier. So I mentioned how if you have like the triangle boundary meshes are a very common geometry representation. But it is still expensive to take that triangle boundary representation and turn it into a tetrahedral mesh. So how do we get the moments of intersecting our grid with some surface? We can compute this integral with the divergence theorem. So what we're going to do, if we do this in 2 dimensions, it might be a little easier. So instead of like computing this, right, we can get just the boundary, and I'm not even going to bother right now. But basically, if we can essentially imagine that like if we take the derivatives of these functions and integrate them with some normal information over the boundary, we can recover the integral of those basis functions over this domain. And so in 3 dimensions, we're actually going to have to do this twice, right? So we can integrate with normal information on the surface, we can integrate the derivative of those moment basis functions on here, and then we have these line segments, and so we do the divergence theorem twice. And so we first get the surface sum, and then we have these line segments for each of these 4 faces, and we do the divergence theorems that second time, and what we've ended up doing is integrating those moment basis functions over this volume represented by the boundary intersecting with a cell. And so without ever having to allocate quadrature points within this volume, we can capture the integral properties of this shape. And this is much cheaper to do than trying to figure out how to allocate tetrahedrons and whatnot. It's kind of cool. Right, so basically the consequences of all this are that the software that I was working on at Intact Solutions was able to operate and perform finite element analysis on a much wider range of geometry than you'd typically be able to do. So like this CT scan example was pretty cool. This is not really possible with traditional finite element workflows, but also we can handle, like I mentioned, G code. So one of the problems in validating parts is that you'll design this nice part in CAD software, but that's not really the manufactured part, right? Like if you're using something like printing, you've got like a tool path, and you get like little bumps from like the plastic deposition and all of that, right? So it'd be really nice if we could simulate on the as manufactured part, but again, that would be really hard to mesh. But the G-code line segments, we can generate nice quadrilaterals for those. We can use those quadrilaterals to capture the moments, and then we can use the moments to perform finite element analysis. And so that's kind of like, there's really big providers of finite element tools like ANSYS, Abacus. These are like what big commercial companies use. Intact Solutions is mostly working on like research grants for the government to show that we can like, do simulation and other kinds of geometry and other kinds of material fields. And that actually is all I had. I think that gets us to about an hour, so that's pretty good. Any other questions?
Yeah, like, are there any constraints on like the mass density function? Like, does that like enumerate to 1?
That's a great question. So certainly if the element was full, we would want the total weight. And it's not exactly